12.1, where I'm going to do all the steps for some raw data and all the steps for what you would need to do a confidence interval and also a t-test for linear regression, and also how to look at it on the calculator. Now, first of all, if you have something like this, raw data, the first thing you would need to check is, of course, your liner. And as we know, that's pretty involved, as you have to graph, scatter plot, you have to find the residuals and all, normal probability plot of the residuals, things like that. So we'd have to go through all of that. So I'm going to leave this room right here for checking my conditions, but I'm just going to, I know that they're going to meet, and I just, I think, like, why don't I jump right into the calculator, so that if you feel like you really know how to find the residuals and all that stuff, you can have that at the end of the video. But so let's say that the conditions are met. And so on the left side, why don't we do a t interval for the slope of the linear regression line. And then on the right side, why don't we do a t-test for the slope of linear regression line. Okay, so I am going to show you how I would do this with my calculator very quickly. So going to the calculator, and I already have the data in the calculator. So now what I'm going to do is I'm going to go to stat, tests. Because I was able to identify the name of this test, that helps me scroll all the way down, and you have to go down a ways past those goodness of fits, way down. Look at how far down you have to go. There is a linear regression t-test. There is a linear regression t-interval. Okay, so if I press that G with my data in L1 and L2, I haven't even entered the predicted equation in yet. And if I wanted it to store the linear regression equation, I could have it store it by hitting vars, yvars, function y1. So now it's going to store it in that y1 location in my calculator, in case when I do the graphs later, it'll be there. And if I hit calculate, it gives me so much information. It gave me the interval, it gave me the point estimate, so that's going to be the middle. It gave me the degrees of freedom. Notice that it took that 16 and went down by 2. It gives me, this is S, standard error for the residuals. It gave me the A, which is the y-intercept. It gives me the coefficient of determination. It gives me the correlation coefficient. Notice that it's negative because this thing is going down. And that's everything that it's giving me. So I can write down all of this information on my paper. It gave me my predicted interval for beta. The calculator says it is negative 0.0019 was the upper level, and negative 0.005 was the lower level. The predicted equation that they gave me was y hat will equal, let's see if I put the slope first, negative 0.003441 x, and then my y-intercept plus 3.50512, where y hat is the predicted fat gain, and that's in kilograms. where the X is the NEA change, and that was in calories. All right. So, and then how might I have gotten all this information myself? Needed the point estimate for the slope. I would need to find the critical t-value for the alpha and the degrees of freedom that we have. I would need the standard error for the slope. So I would need those three things in order to do this. I'm going to do those in just a bit. I do know what B is. I will find the critical t for a 0.05 divided by 2, comma, 14 degrees of freedom. And I will show all the work for finding that standard error of the slope. But before I do that, I want to write out the information for the test, just that you have that, and I want to show you how I would do that with the calculator. So when I do that with the calculator, I am going to do the null hypothesis is always that there's no evidence of a linear regression relationship, or that there's not a linear relationship, but we are specifically looking for here there being any kind of a linear relationship. So we are looking for this. So this is any type of linear relationship. So that's a two-tailed situation. I'm going to use the calculator and have the calculator tell me what the p-value is for this. So we can see that. Where I am going to hit stat tests, and I'm going to scroll down to now this time the linear regression t-test, where I have my data in. And I am going to do this at not equal to. And I can even, it'll still store the equation in the same place. It's going to be the same equation anyway. So here is my test for my equation of there being any kind of relationship. There's my t-test statistic. There's my p-value. Again, the degrees of freedom is 14. And then you can see here's the y-intercept and the slope as predicted by the model. Standard error for the residuals. And again, coefficient of determination and correlation coefficient. So that looks like I have evidence of, see, that's very much less than 0.05. So I have evidence that there is, in fact, some type of a linear relationship between NEA change and fat gain. Let's write this information down. Okay, the t-test statistic was t is equal to negative 4.6418. The probability that a t goes below, because think about where that would be on your graph, 0 being the middle, negative 4.64 right here, you're doing this, but we are doing two-tailed. So going below a negative 4.6418 would be, well, it'd be some number, but we're going to double it, and that result would be 3.8095 times 10 to the negative 4. So that is significant evidence at the alpha equals 0.05 level. So how would we have found this by hand? I would have had to find my t-test statistic, and that would have been b minus the hypothesized value, which is going to be 0, over my standard error of my slope. And so I would have the b, which I would get from the equation, subtract 0, and I would need to know what that standard error was right here. So I'm going to need those numbers. So let's go and figure out what those numbers are, and we'll be able to use them for both the interval and the test. So first of all, off of the calculator, we got, by doing the linear regression, we get our beta, which was negative 0.00344147. So that number would go right here in this location, as well as right here in this location. My critical t value, if I use the inverse t, so if I go inverse t for a 0.025 comma 14, the calculator will give me a value of 2.1448. So that would have gone right here in my confidence interval situation. Okay, so now how would I have found the standard error of the slope? Recall from your formula sheet, you would need the standard error for the residuals. You would need the S sub x, the standard deviation for x, and you would need to know the square root of n minus 1. Now this would be the same for both situations. See, we also need that over here. So first of all, the calculator did tell us what S was, the standard deviation of the residuals. I'm also going to show you how I could have gotten that by hand on the calculator, because the standard deviation of the residuals is the sum of the residuals squared divided by n minus 2. That formula is on the formula sheet. We know from the calculator that it came out as a 0.739852873. I don't know why I'm writing so many things. But anyway, that would have been the standard deviation of the residuals. I'm also going to show you how I would have used this right here in order to find this number right here. If I use my calculator, and I will show you how I get this, what's the standard deviation of x using my 1-var stat, I would have found 257.6567484. And then, of course, n minus 1 would be 16 minus 1, which is 15. So I could put these pieces together, 0.739852 8737 over 257.6567484 square root of 15, and I would have gotten a standard error for my slope of 0.000714. That number right there, that standard error of the slope, whoops, this thing, sorry about that. That standard error of the slope would have gone right here in my test statistic. It would have gone right here for my interval. That number, this number right here, would go in those two places. When I punch in that result, I would have gotten that test statistic of negative 4.6419. Okay, so that's how I would get that. So now let me show you how I would have done this on the calculator to get these informations. And of course, you would write your conclusions for both of these, but I'm just showing you with calculator use how to do this. Just to remind us that this was the equation that we got. This is our standard error of our residuals, which I was kind of lazy in my units. That would be kilograms because it should match y. And this is my standard deviation of x, which of course should match the x units. But, okay, so let's go over to the calculator. At some point, we have to put our predicted equation into the calculator in order to figure out what the residuals are. So we've got our x, we've got our y. Here's where I'm going to put the predicted y. So typing that in, 7, then my L1 list, plus 3.505122.916. We probably don't really need all those places. Okay, so there's my predicted equation. There's my observed. So the residuals go observed, and that's what's nice about having this order. Observed minus predicted. So there's my residuals. Now, if you think about what the S equation is supposed to be the sum of the residuals squared over n minus 2, and then the square root of that. So how might I do that? I could square my residuals in this column here. So this is going to be L4 squared. And then I can go out of this and I can say, let's do stat calc one var stats, and I can do that on my L5 list. That's going to give me right here, that gives me this number 7.66335 over, well, n was 16, so 14. That number, when I punch that in, I'm going to get that right there. Now, if I had done this with my L4 list, instead of the L5 list, if I had not bothered with squaring it, you can see that I get the same thing here in the sum of the x's squared. So it could have taken that number and I could have written that number from just doing the L4 list as well. So when I quit from this and I type in 7.66335 divided by 14, and then I take the square root of that, so raise that to the 0.5, or use the square root, whatever you prefer, and then see, that gets me my standard deviation, standard error for the residuals. So that's how I could get that number, by using a calculator, by using the formulas that you see on the formula sheet. You can get that. Now, how about this number here, the standard deviation of x? Well, that's fairly simple, just going into here and just saying, let's do this on the L1 list, which is my x list. And if you go down on there, make sure you don't use the population value, use the sample value. And so you can see that that matches right there exactly what you see on the calculator. So that could have given me those two numbers, which then I can put together to get my standard error of my slope, which from the formula sheet, it says that I need to take my s and divide by my s of x and the square root of n minus 1. So I am going to take those numbers that you see here. Let me clear this. Okay, so take those numbers, that 0.7398527, that's probably enough, divided by my standard deviation of x, 0.6567. Okay, and then I do need to divide by the 15. So I'm going to hit divide because I forgot to put parentheses around it. So I'm going to divide by 15. Oh, it has to be square root of 15. Let's go square root of 15. Gotta get rid of this. Okay, let's see what happens. And that matches my standard deviation of the slope, or standard error for the slope. That, remember, I had written it like this on your paper before, 0.00074114. But scientific notation or moving the decimal, it's the same thing. So probably just easier to write it like that, to be honest with you. So that's how I got all those things. And now that I have the residuals in my calculator, let's go back and go through what I would have done for the graphs. So going back, going to my stat plot to check my liner. So this is now to check liner. Let's check the L first. So I would have done a scatter plot of L1 and L2. So graph it. And there it is. Remember, I had stored the equation. That's why you see the equation there. So that is looking linear. Form is linear. Direction is negative. Strength, we saw the R value was, I can't remember what it was now, but they did give us an R value, and I think we said that it was moderate. Okay, so that was checking the L. Independent, I would say that 16 is less than or equal to 10% N, although we may have already done this. Okay, so those are those two. Now let's check the nearly normal. We need the residuals for that. So let's go in and check the residuals. So going to our scatter plot, this time we are going to do a, well, let's do the histogram. And this is going to be for our L4 list. I know I'm going to have to, because if I just hit graph, it's going to give me an error because like it's way out of the range. So I'm going to hit zoom. So let's quit. We'll go zoom 9. And there you go. There's my histogram with that pesky line equation showing up. Seems fairly symmetrical. You would do a rough sketch of this. Now let's check the normal probability plot of the residuals. Oh, and also checking for outliers because those are never good. So let's just quickly check for outliers. Go to the box plot. Whoops, this one, modified box plot. Again with the L4 list, so graph that. Zoom 9 again, just to make sure. Okay, yeah, so I don't see any outliers. No outliers. Now let's check their normal probability plot. And again, I'd be drawing all of these things, so that's going to be this last option here. And let's graph that. And I'm going to zoom 9 just to make it look a little, zoom 9. It looks reasonably straight to me. So that is good for our normal probability. And that's, of course, the most important of our checks anyway. So we have established the LIN. Okay, now we need to check the equivariant scatter. So let's check that. Going back into our stat plot, this time it's going to be a scatter plot. We want the residuals on the y-axis. We want the x list. So see, I had to change that to the x list. And I want the residuals, the L4 on the y list. Now, if I just hit graph, I bet it's going to give me an error message. Oh, no, it didn't, but I still can't see anything. So zoom 9. And so looks like pretty much equivariant scatter. So we had to do a scatter plot. Let's see, move this up here, scatter plot. And we're looking for that equivariant scatter, you know, and I think it looked good. And then, of course, your last thing that you're going to check, see there, you can see it again. And then last thing you're going to check is if it's random. And so, and it was given that it was a random sample. So it looks like we were able to accomplish all the things we need to do for inference on the slope using a confidence interval and also using a t-test.